All right, so for this last portion in the 4.3 notes, we're going to talk about some special logs and some notation. So first of all, there are two special logarithms. One's called the common log and one is called the natural log. So the common log is simply a log base 10. Kind of like when we have a cubed root of a number. If we don't put anything under that, anything in this spot here for the index of a radical, it's assumed to be 2. So the assumption is if you don't see anything, it's a square root. Well, same with a log. If you just write a log of the log of x, and you don't put a base down here in the subscript, that base is assumed to be the log base 10 of x. Okay? And our calculators, I mean, this is a very standard convention. Our calculators, if we just say the log of x and we don't put a base in for the log, it changes it to base 10 because that's the assumption. So that's one special log if you want to just shorten it up and not write down the base. The other one is the natural log, which is a log base e. That is an ln, not an in. So this is the natural log of x, which simply means the log base e of x. Okay? And this is the log I use mostly in class. This is called the common log because it's supposed to be the most common, but really the most widely used, most commonly used log is the natural log, or the log base e, because of that special number e and how it occurs in nature and with growth like we talked about before. So please try not to get confused. I know at first it's confusing. You're like, what is a natural log? I don't understand it. It's just a log base e. So let's express these in exponential form. There is no base, so I know the base is 10. 10 to the second power equals x. By the way, we just solved our first log equation. Boom. A log equation is an equation that's got a x inside the log, the variable inside the log. To solve it, one way to solve these equations is just to write it in exponential form. So x has got to be equal to 100. For this one here, this is a natural log, so the base is e. E to the x power equals 5. That's it. They're just asking us to write it in the other form. Evaluate. So this is the log base 10. So the question is, 10 to what power gives me 100,000? Every time you raise 10 to another power, it gives you another 0. So this would be to the 5th power. This one here, e to what power gives me the 4th root of e? Well, the 4th root of e is just e to the 1/4, so this is the 1/4 power. Decimals aren't your friend. This is the log base 10 of 1 tens, hundredths, 1,000. 1 over 1,000. So 10 to what power gives me 1,000? Well, 10 to a negative power puts the 10 on the bottom of the fraction, and you raise it to the 3rd power to get 1,000. Again, if you don't like doing these in your head, that is fine. If you don't want to do it in your head, then this is what you're going to have to do. 10 to the x is equal to 1 over 1,000. 10 to the x is equal to 1,000 to the negative 1 power. Move it up. 10 to the x is equal to, this is 10 to the 3rd. If you take a power of a power, you multiply the exponents, 10 to the negative 3. If 10 to the x is equal to 10 to the negative 3, then x is equal to negative 3. So if you like that better, by all means, you go right ahead and you do that. As seen earlier in earlier examples and the graphs, you can't take the log of a negative, nor take the log. All right, so I'm sorry, I got distracted here. We can't take the logs of negatives or zeros. You can only take the logs of positives. So it says try entering the following into your calculator. So what happens if we take the log base 2 of 0? Log base 2 of 0. It says undefined. Okay. This is kind of synonymous with like dividing by 0. Like you just cannot do it. I mean, it's not the same, but it's like that. What happens if you take the log base 2 of negative 1? What is the log base 2 of negative 1? Now it says non-real result. So this kind of implies, well, if you read it, it would say that that if you take the log of a negative, it actually is an imaginary number, which is kind of interesting. I personally don't know a whole lot about it. I've never really studied it, but if I put it in rectangular mode, I type in the same thing. So if you take the log base 2 of -1, it kind of gives you a pretty nice little thing here. It's pi. Go figure that pi would show up in this weird thing. Log base 2 of e. Now I didn't have a base e, but that e shows up here times I. So this is kind of a pretty interesting equation that it involves I, the imaginary unit, e, the natural number, and pi. In fact, there's a equation, maybe we'll do it later in the notes, that is, it's called the Euler equation, and it kind of relates pi, e, I, 1, and 0, which is kind of an interesting and well-known. Regardless, for us, this is just going to be undefined, okay? You can't take logs of negatives. Find the domain of the following function. So I want to find out what x can be. Well, I can only take the logs of positive, so whatever is inside the log has got to be greater than 0. It's kind of like whenever when we did domains of radicals. If you recall, we always said whatever's inside that radical has got to be greater than or equal to 0, because you just can't take the square root of a negative. So this is kind of the same thing, only we don't have the equal to part because you can't take the log of 0. 10 has got it. So x has got to be less than 10. It's simply that data set. So the domain of our function f is -infinity to 0. Oh, sorry, to 10. Easy peasy. I would encourage you guys to get used to setting these things up and not trying to do it in your head, just to make it kind of more procedural. Example, find the domain of the following function. So this one you're not going to be able to do in your head, I wouldn't think. Natural log of that expression. Well, whatever's inside the natural log, that expression has got to be greater than 0. So we need to solve this. How do you solve a nonlinear inequality? Sign analysis. All right, so let's factor out a -x squared. Leaves me with a -4 plus x squared. You rewrite the inside, so the x squared is first, so I can factor it in my comfort zone. -x squared, x plus 2, x minus 2. Let's find the critical points. Set it equal to 0 to get the critical points. That would be x equals 0, -2, and +2. And now let's do the sign analysis. -2, 0, +2. 3 values divides the number line into 4 regions. Let's pick a test point on each of these regions. -3, -1, +1, +3. And let's plug each of these values in and get a value for our sign. So I'm going to treat these as 3 factors. I'm going to call this 1 factor, factor 2, factor 3. So I'm going to get 3 signs. If I plug a 1 in, 1 squared is 1, negative is a negative, 1 plus 2 is a positive, 1 minus 2 is a negative, 2 negatives make a positive. Now, if you want to plug in those other values, feel free to. I do like to use that shortcut and kind of talk about multiplicities here. So if I hop from here to here, if I hop across this 0, that was from this factor. The multiplicity of this factor is a 1, so it will change to a negative. You don't like that? Plug in all the points. If I hop over to 0, that's this factor. This factor's got an even multiplicity. Double multiplicity. So that means it's not going to change signs. And if I hop across the -2, single multiplicity, it's going to change signs. So my solution, or my domain, is going to be all the values of x that make this expression greater than 0. So I don't want it to be equal to 0. Open points on the critical points and greater than 0. So here to here and here to here. So the domain of f is equal to exclusive -2 to 0 in union with 0 to 2. Okay? 10 minutes, and I want to type that in the calculator to see and show you. Who cares? I'm not going to type. You should graph this in your calculator. I bet you will only see graph on these intervals, and you won't see anything else. Find the domain of the following. This one's just got 3 different pieces. Each one of these has got a little restriction associated with it. So let's just find those 3 restrictions and then put them together into one final domain of possible values. Log, well, 5 minus x has got to be greater than 0 because you can't take the log of 0 or negatives. On the bottom, the bottom can be positive, the bottom can be negative, but the denominator cannot be equal to 0. And then for a radical, x plus 9 has got to be greater than or equal to 0. Okay? 3 different restrictions for 3 different reasons. Add x, so x has got to be less than 5. I guess, I don't know how we want to do this. Factor it or move the 9 over? I guess I'll factor. So if this can't be 0, then x cannot be positive 3 or negative 3. And x has got to be greater than or equal to negative 9. So if we put those 3 things together, on one hand, x has got to be less than 5, not equal to 5. And x has got to be equal to negative 9 or bigger than negative 9. And it can't equal these. So those are the values that x can be. So the domain of my function f is inclusive negative 9 to negative 3, exclusive negative 3 to positive 3, exclusive positive 3 to exclusive 5. There we go. Mostly review, but we're just adding logs into it. And that is the conclusion for section 4.3.